So warm greetings to all of you. This is the first lecture of Chemical Engineering Thermodynamics. This is meant for the second year chemical engineering students who have undergone first introductory course of engineering thermodynamics. This particular course will be assisted by my teaching assistants Mr. Manish Maurya and Dr. Praveen Kumar. I can be reached over phone by given this number, and I can be also reached by email at this ITK email address. Okay. So I am in the Department of Chemical Engineering, IIT Kanpur. Okay, so let me start with a very philosophical question: why thermodynamics for chemical engineers? You know, whether it's a good or bad, or whether you like it or not like it, all physical processes observed in the universe follows the laws of thermodynamics. So this is something which we have to deal with it, and chemical engineers cannot avoid that. In general, thermodynamics plays an important role in various branches of science and engineering, but for chemical engineers it is relevant particularly to the industry dealing with chemical processes, and particularly for materials where the phase diagrams and the properties becomes an important aspects in the design of such processes. While we will talk about the modeling of the various different physical process, such as for example the separation of the fluids into vapor and liquid, or liquid phase diagrams, and where the thermodynamic aspects plays an important role, but we can start with the very simple questions, and the questions such as what is the solubility of CO2 in a solvent. These are some questions which are relevant for chemical engineers because it plays an important role in industrial applications, but fundamentally also it plays an important role to understand, for example, are two polymers miscible or compatible with each other, where certain process feasible at all, or does a fuel cell has a higher theoretical efficiency than an engine, what is the best separation we can expect from distillation, what is the minimum amount of energy necessary to achieve such separation. Okay, and we can keep going on because the questions are unending, but I will just thought to start with a basic set of questions to illustrate where the chemical engineering thermodynamics plays an important role in terms of addressing some relevant questions, particularly for chemical engineers. For example, what is the explanation of olive oil dissolves in the vegetable oil, likes like, but not in water? Okay, this you can think from the thermodynamics point of view as well as or from the physical chemistry point of view. Now take a question, for example, certain molecules in the gas phase can react only when they are adsorbed on the catalytic surface. However, if we increase the pressure in the gas phase, how will the amount of adsorption change? How can this experiment be used to estimate surface area in porous materials? Can the thermodynamics address such a questions? Okay, or we can look at the aspect of the reaction. If the reaction is feasible, does it proceed to completion? Okay, so some similar kind of questions you can list down, and the idea behind learning this particular subject is to equip ourselves with tools and abilities to address such fundamental questions using theoretical means. Okay, and this is something which we are going to learn in deep, in particular this course. We will divide this course in two aspects. One, the first part will be trying to build up the fundamental aspect of the chemical engineering thermodynamics, where we will be focusing more on the philosophy of the development of potential functions, in general all the thermodynamic rules, and trying to build up the knowledge and later on apply to various different applications related to chemical engineering thermodynamics. As we already know, introductory engineering thermodynamics, that this is a subject of great generality applicable to systems of elaborate structure with complex electrical, mechanical and thermal properties. Essentially it means that this is widely applicable. However, in chemical engineering we will be to start with dealing with only the thermal properties, okay, where the properties change as we change the temperature and basically also as we change the pressures. Okay. Later on we will be looking into some changes in the compositions and how does that change the properties of the system. To start with, we will be focusing only for very simple systems where the mechanical and electrical properties are simple. That means, the restriction on the types of the systems considered in this particular course is not limitations of the thermodynamic theory, but are adopted merely for simplicity of exposition. So, basically it tells you that what we are going to develop, though, is for the very simple systems where we are not going to take a complex electrical and other kind of external field, just for the sake of our expressions to be very simplified, so that we can understand the theory. However, that is not the limitation of the thermodynamic theory. So, in other words, we will restrict our attention to simple system, which are nothing but macroscopically homogeneous, isotropic, uncharged, that are large enough so that the surface effects can be neglected, and that are not acted on by electrical and magnetic and gravitational fields. Okay. So, our systems are going to be very straightforward, homogeneous, isotropic and uncharged. Okay. So, you can elaborate this, that there will be no electrical coordinates in our system. System is uncharged, neither electric nor magnetic dipole, quadrupole or higher order moments we will be considering in the system. All elastic, shear component and other mechanical parameters are 0, and there will be a definite chemical composition given by the volume and number of moles of different species. So, the composition will be fixed. Okay. So, this is the idealization of the system in our consideration. Now, in order to elaborate more on this, I will just briefly describe a few things that will be dealing with variables. The variables such as mass, volume, temperature, pressure, density. Now, before I go further, we will just describe two aspects of such variables or the properties, which can be divided into extensive and intensive properties. So, extensive properties of variables is the one that is linearly dependent on system size, okay, which you can clearly see the case of mass and volume in this case, whereas intensive variables are the one which are independent of system size, which in this case is temperature, pressure and density. So, what we did here, that we took a system having this set of variables or so properties, and we divided it into two halves. So, the volume get divided, but the rest of the variables remain the same, and those kind of variables are called intensive variables, and those which gets affected by this changes in the system size are the one which are extensive variables. Now, extensive variables or parameters play a key role in thermodynamic theory. Okay. So, with this definition of variables, I will now describe the postulates or the foundation of the thermodynamics, which are based on various different postulates to start with. Okay. So, we will start with the first postulate of the thermodynamics, and it says that the macroscopic system possesses an internal energy which is U, that is subject to a conservation principle, okay, and is also extensive. So, this is the first postulate. So, the idea is to understand the foundation, how it was developed over the years, and now which is considered to be a sound, and this is what the theory view of thermodynamics we consider. Now, one of the question is where this particular internal energy of the system stored. Now, this we know from our introductory engineering thermodynamics course, that U is stored in sensible vibration of atoms, rotation, translation. Okay. So, this is nothing but sensible energy, and then you have this latent energy and chemical and nuclear energies. Okay. So, internal energy has property just like other forms of energy, which essentially means this can change from one form to another form. Okay. So, it can be exchanged between different systems, converted to and from other forms of energy, and can be used to extract work. For the case of this conservation principle, which basically it means that if we add up all the forms of energy in an isolated system, then the sum total of those energy is constant, although one form might have increased while another form might have decreased during a process. Say for example, kinetic energy becomes internal energy. So, it means that for an isolated system, all forms of energy, if you add it up, basically should be constant, whereas one form of energy can change during this process to another form. Now, at this point it is important to emphasize that this knowledge of conservation principle is not, though it may look like very obvious now, and half centuries to develop. So, it has been a very slow and laborious process. The first recognition of conservation principle repeatedly failed, but in each case it was found possible to revive it by the addition of the new mathematical term. Okay, and during this 2.5 centuries, people have come with the new terms in order to have this conservation principle to hold, and this is something which suggests that this has become an extremely valuable process in which new kind of terms have been evaluated. For example, consideration of the charge system necessitate the addition of the Coulombic interaction and eventually of the energy of the electromagnetic field. In addition to that, in 1905, Einstein extended the principle to the relativistic regions, relativistic rest mass energy. In the 1930s, Enrico Fermi postulated the existence of a new particle called neutrino solely for the purpose of retaining the energy conservation principle in nuclear reaction. So, during these 2.5 centuries, okay, this conservation of energy has become the significant achievement in the evaluation of the physics, and that is what it tells you that this knowledge which we have now is basically due to a lot of work done by scientists in during last few centuries. Okay, so coming from this philosophically now going to more practical aspects here, we will start with a very fundamental question here, that why the density of pure water at 1 atmosphere and 25 degrees Celsius is always 1 gram per centimeter, irrespective of wherever you take it from, whether it is from Ladakh, whether it is from Kanyakumari, you bring it to the room temperature and pressure, you are going to get the same density, that is 1 gram per centimeter cube. So, it tells you that this is a stable state of water at this particular temperature and pressure, which is called equilibrium state. Okay. So, thermodynamics particularly deals with this equilibrium state, and we are not going to talk about the dynamics of the states between such state. So, in general thermodynamics which we are going to talk is basically equilibrium thermodynamics, okay, where only the equilibrium states are going to be considered. So, thermodynamics does not say how long it will take to reach equilibrium of what path the system will attain the equilibrium. So, this is something which is extremely important. So, we do not talk about the transient path which will be taken by the process in order to attain the equilibrium state. Now, this another important thing is, irrespective of our systems of different nature, it may take enormous time or slow time, or some processes may be very fast, but all the systems tends to have a natural tendency to reach a time invariant state called equilibrium state. So, all the systems tend towards the equilibrium state. Okay. Now, this is the observation we have. Now, so this leads to the second postulate, that there exists an equilibrium state of a simple system that macroscopically are characterized completely by the internal energy, which is U, the volume V, and the moles number N1, N2 to Nr of each component. So, in other words, this postulate says that if you define U, V and mole numbers, you are basically defining the state of the simple system. Okay. So, if U, V and this means your N1 till Nr, if defined, which means the equilibrium state is fixed for that particular system. Okay. So, having said that, now let me just quickly go through the basic definitions which we typically use in the thermodynamics, and some of you or many of you have already seen these definitions. So, but for the sake of completion, I will just go through quickly. So, when we talk about thermodynamics, we are typically interested in the system. Of course, system is separated from the surrounding through a fixed or some kind of fictitious boundary, okay. But the system is basically nothing but a quantity of matter or a region in space chosen for the study, okay. And the surrounding is basically the mass or region outside the system, and the boundary is a real or imaginary surface that separates system and surrounding. So, this is how we define it, but the boundary could be of many types. The more important thing is the boundary has a 0 thickness, it has 0 mass or volume, but it can be fixed or movable, flexible or rigid, okay, insulated or adiabatic, which means insulated means it does not allow any heat to transfer. Insulated or adiabatic is basically synonymous. So, insulated it does not allow any heat to transfer, and adiabatic of course that no heat is being transferred, and the other possibility is conducting or basically dithermal. Okay. You can also have permeable and impermeable, which essentially means that it may allow some species to transfer from surrounding back and forth, okay, or impermeable, which means basically the mass cannot flow in and out from the system. Okay. So, this is a type of the boundary which controls the nature of the particular system surrounding interaction. Now, in addition to that, we can specify kind of system by or the surrounding in terms of closed, open or isolated system. So, for closed system, okay, which could be in this form, the mass interactions are not allowed, that means no mass can enter or exit from the system. Energy however can cross the boundary. Okay, volume on the other hand can be fixed or it can actually move also. You have a piston, movable piston, that still would be a closed system. In case of isolated system, no energy is allowed and as well as no mass is allowed. Okay, so in case of open system, such as for example the compressor, turbine or nozzle, in such case both mass and energy can cross the boundary of the control volume. Okay. So, typically we define this kind of dotted line as a control volume, which is used for to define open system. Okay. And it can have this imaginary boundary or it can have this real boundary. This is the case for the nozzle, where both mass and energy can cross the boundary. Okay. So, here the control volume is an arbitrary region over which you can do this thermodynamic analysis. Okay. It can be fixed in size and shape or it can have a movable boundary. So, these are the examples of open system. Just for example, heater, water heater here is basically continuous flow of cold water and heater hot water, essentially leading to an open system kind of example. Now, the system has properties as we discussed, the variables like pressure, temperature, these are basically the essential elements of the system, which is basically nothing but the properties. So, system may consist of many species like a mixture of a nitrogen hydrogen in a reactor leading to ammonia at a given temperature and pressure. Now, if you want to understand the state of the gas mixture, which could be a mixture of all these three gases, or in general if the conditions are changed, the reaction may change and leading to a different state. In order to predict such state, you need to know the properties of the material. Okay. So, which essentially we will be elaborating more later part of the course, but one of the important thing we wanted to emphasize here is that a property should have a definite value when the system is in a particular state. Okay. For example, if you fix your temperature, pressure for a pure system, it will have a specific state, okay, and leading to a specific internal energy. So, we will be elaborating this. So, I am taking this base that you have already undergone the first introductory course of engineering thermodynamics. So, a property should have a definite value when the system is in a particular state, okay, and the value of the property should be determinable irrespective of how the system is brought to the particular state, that is it should be independent of the path. So, if Z is a property, then from the initial to the final state along a path will be simply, it can be given by the difference in the Z value. So, in such case dz should be an exact differential, that means thermodynamic property Z is a point function. Okay. So, for example, a change in the process, okay, where the volume changes by Vf minus Vi will be given by delta of simple V. So, in such case V is basically property because it just depends on the final conditions of the state, okay, and hence is a point property or point function. Now, let me just quickly go through the process also. A process basically is nothing but any change from one equilibrium state to another state. For example, this state 1 and state 2 along this green line is nothing but a process. Okay. This is drawn on a property A versus property B graph. Okay. This is called process diagram. The path here is basically a series of these dots which are equilibrium point. That means these are so slow changes that we can draw a line or draw a curve along this dotted line, and the assumption is that the process is extremely slow and each point is very close to an equilibrium state. So, these are called quasi-static or quasi-equilibrium process, okay, which will be for the case of the slow compression or slow expansion. But anything we have such as very fast compression, we cannot draw such process path for very fast compression. Okay. So, these assumptions we consider, this is something we consider in our description of the thermodynamics part, because it is easy to analyze, okay, and later on we will be discussing about that this is the case where the work producing delivers maximum work and work receiving devices receive minimum work in order to operate. Okay. This is the process diagram, I have already gone through that. Now, process diagram is very useful in visualizing the process, okay, such the common properties are TVP. So, you can have plots such as T versus V, T versus P, V versus P and so forth. Okay, process path is used only for quasi equilibrium processes and is not useful for non-equilibrium or very fast process. Now, in addition to that, you can have many different processes where you can fix the temperature, pressure, volume. This is isothermal, isobaric and isochoric, and as well as you can have a process during which the initial and final state are identical, such as cyclic process. Okay. So, this was a very quick recap of the definitions which we already know, but just for the sake of going through that, so that the terms becomes more easy for you to understand. Now, having done that, let us now ask a very fundamental question, and that is about this energy. Is this energy macroscopically controllable or measurable? Okay. So, can we measure the energy? That is the question which we would like to address. Now, consider a box having ice and water, and you are looking at, you are observing the ice, or your interest is to melt the ice. By providing this stir, okay, so you are doing a mechanical work on the system, which is basically the ice and water. Okay. So, ice melts rapidly with stirring, that we of course can visualize and understand. So, we can also correlate that the melting of the ice is related to the energy or mechanical energy which is transferred to the system. Now, if this particular system is isolated, okay, or in other word insulated, then whatever the melting or the energy transferred in order to melt would be given by the mechanical energy. Okay. Now, in summer, if let us assume that this is not insulated, in this case the ice melts spontaneously without any work. So, in other words, there is no stir in this particular case, and in spite of that your ice will melt, particularly in summer. Now, this is something which you can imagine that the energy may have transferred in the form of some heat, okay, from system surrounding to system, right. So, now you can consider also that can you control this heat transfer by changing the wall of the surface of the container. Okay. So, the rate of the melting of ice can be reduced if you change, let us say if you consider very thin metal sheet, then it will allow heat transfer, okay, that so it will be like dithermal. However, if you increase or if you replace by a metal sheet by a thick glass, then it will reduce the rate of the transfer from the surrounding to the system, and if you replace that by a Dewar wall, it will become more and more insulated. So, you can control this rate of melting of ice. Okay. So, this is something essentially what it means, that by changing the constraints through wall, we can control the energy of the system. Okay. Another word, you can find out precisely also the energy transfer. This is something which should become clear in a later slide. So, in summary, the walls can control, and therefore, energy is microscopically controllable. Okay. So, this was the first question, that can we control the energy. The second question is, can we measure the energy. So, controlling the energy requires you to manage the boundary or the walls of the system. Okay. But what about the measurement of this energy? So, what we can do is basically we will stop here and we will take up this measurement of the energy in the next subsequent lecture. Okay. So, have a good day.